If asked in interview, do you know how many types of power dissipation are there in CMOS VLSI design? If asked further, do you know what are the methods or approaches taken in VLSI design to handle all of this kind of power dissipation? For a power-packed knowledge session, please watch till the end of this video. Hey guys, welcome back to the computer screen. In today's episode, we are going to discuss the below points. Power analysis of CMOS circuits. Next, we will zoom into the different parts of it like the dynamic power dissipation, short circuit power dissipation, and static or leakage power dissipation. So first, we will focus how the power is dissipated. And next, we will talk about total power dissipation, including all of this in consideration. Next, we'll talk about low power optimization. So below this line, we are talking about the CMOS methods applied in VLSI, how to manage the power. That means how we design a low power circuit and what methods we apply there to save the day, means save your battery and save the power. Next, we'll go in explicit detail of dynamic voltage and frequency scaling, which is abbreviated as DVFS. Next, we'll talk about clock and power gating. That's the menu for today. Without any further delay, let's begin. Introduction. Low power design is the need of the hour, means we are at a time when the low power devices, whether it is your smartphone, smartwatch or wearable medical devices are there, they need a low power design. What is a low power design? A low power design makes sure that your battery do not run out. You may argue that we use a rechargeable battery. Yes, we do. But what if you are traveling and your rechargeable battery goes out of the charge and you do not have a charging point to recharge it? So for that, the low power design is the need of the hour. Means today, whatever time point we are standing, the low power design is very much needed thing. The rapid growth of smartwatch industry, smartphone industry and wearable medical gadget industry has enforced that. This is we just talked about. Because why it is the need? Because all these things are now with almost every alternative person you find. An IC's total power consumption comprises of two types, static and dynamic. This is the broad category. Static power typically comes from the leakage current and DC current sources. Dynamic current consumption, which is frequency dependent, often dominates the total power. So the dynamic power is mostly dissipated when the device is operated at high clock frequency. That means it's in its digital mode of operation or it's in action. EDA tool vendors, that means the companies which make the software for VLSI designs, now offer low power optimization tools inbuilt and methodologies together to handle low power design. So why I say about the optimization tool and methodologies? Are they different? In some case, they are different. In some case, they are not different. Some companies, they implement the tool and the methodology together. And in some cases where the tool cannot have all of them together, there the different methodologies are implemented by the end user using the different tool options. So here we are done with our introduction. Let's move on to the next slide. Power analysis of CMOS circuits. The total power consumption of CMOS circuit consists of three components. First, the dynamic power component. Next, the short circuit power component. Next, the static power component due to leakage. Now, leakage means this is the off-state leakage. Power can be estimated at a number of levels which include, that means when you are having a VLSI design in your hand, you are as a designer, as a VLSI engineer, or you are maybe a verification engineer, whatever your role, you have your design in hand, how you can estimate the powers. Circuit level power estimation using a circuit simulator such as SPICE. This can be done. Static power estimation does not use the input vectors but may rather use input statistics, which is very similar to the static timing analysis where everything is static. So there is a basic difference between a static analysis and a dynamic analysis. In dynamic analysis, everything has to be simulated live with respect to the time. That means the time marker proceeds, you give a start time, you give a finish time, and all the values for all the nodes, the KCL, KVL, everything has to be calculated, and according to the power calculation formula, the power has to be calculated. That is the dynamic one. Whereas in static mode, what happens that you have some predefined or pre-logged data based on which you calculate the power. That is the static power estimate. Next comes the logic level power estimation, often linked with logic simulation. So whenever you are doing the RTL simulation, that is the logic sim, at that time you do also do the power estimation. We have an entire series on UPF, Unified Power Format, regarding this, how we do that. In case you have not watched, please go ahead and watch that series from the playlist page, or alternatively, please look into this video description for the link to the UPF series. Analysis at the register transfer level, fast, high accuracy capacity, but not accurate. So yes, obviously we do not have the backend, that means the layout and the parasitics ready, so that the actual power drop is not calculated at the RTL level. However, at least some estimation can be done, and accordingly some modifications can be done, which may help you to make your design a less power hungry circuit. The power dissipation in circuit can be classified into three categories such described below. So in next couple of slides, we are going to describe all these type of power dissipation. Let us look into the types of power dissipation first, and then we will talk about the methods of recovery to the VLSI design. Dynamic power dissipation. Due to logic transitions causing logic gates to charge or discharge load capacitance. So this is for the dynamic power dissipation. Let us understand with the figure. In the figure, the capacitive charge characteristics of the common CMOS inverter is shown. So the charging is done in this path and the discharging is done in this path. So this way the dynamic power dissipation happens. So you can see this is our load and this is our CMOS inverter. The dynamic charging causes power consumption to be directly proportional to the clock frequency. So this is very important. The dynamic power, that means when the circuit is in action or in operation, the power drop which we have just shown here accumulatively, that means for all the CMOS combinations inside the VLSI chip, are calculated together for the total power consumption, that is the total dynamic power dissipation. So this is the dynamic power dissipation, and more the clock frequency is, more the dynamic power dissipation. That means whatever power we are here in this zone, that means including the charging and the discharging zone happening, that is happening for the CMOS, and the charging and the discharging happen in a particular complete cycle. So if we have more cycles, that means more frequencies, that means we have more amount of dynamic power dissipation. So that is the funda of this dynamic power dissipation. We are done here. Let's move on to the next slide. Short circuit power dissipation. In a CMOS logic, P branch and N branch are momentarily shorted as logic gate changes state, resulting in short circuit power dissipation. Let us visualize this. Here you can see our CMOS combination with the PMOS and NMOS is there, and when the switching is happening, right, at some point of time, here the entire path is short circuit. So the short circuit current flows. So that small amount of short circuit current results in the short circuit power dissipation. Now you will talk that, okay, this is a very small amount of power. Right, here we have the description. The power is consumed because of the momentary current flow that occurs both transistor conduct during a logic transition. So when both are in conductive state, that means this and this. In CMOS, generally either this one is conducting or this one is conducting, but we have a very narrow window of time when both are conducting, and that time the short circuit current and hence the short circuit power flows. This is called the short circuit current. So here we have just shown it. Now let me discuss. You will talk, okay, this short circuit happens in a very short while. Why we are focusing on this? See, you have the clock operating in a fast mode. So if some point of the clock this short circuit is happening, this short circuit is happening repeatedly at each t, that is time period, occurring through the clock. So the entire total result of the power dissipation over the whole time, over the entire time of the operation of the device, all these small short circuit power dissipation or the small power dissipation are summed together to have a larger value. That is why the short circuit power dissipation is very important. Here we are done with the discussion. Let us move on to the next slide. Static or leakage power dissipation. This is the power dissipation that occurs when the system is in standby mode, not in powered mode. That means your device is in idle mode. You are using a smartphone. So you are touching the screen of the smartphone or your smartwatch. That time it is in the active mode. Whenever you turn off the screen either of your smartwatch or smartphone, you do not actively use any app, and hence the thing is in idle. So this is a standby mode, and sometime you will see that it goes to some power saving mode or so. These modes we have talked about in a particular episode of Q&A a power mode versus power domain. So that was the question asked from a viewer and we have discussed. So link is provided in the description. Here is the figure. The subthreshold region is regarded as an undesirable characteristic of the MOS transistors that appeared as a DC leakage current in the CMOS digital circuit. So here we can see that in the NMOS we have the subthreshold leakage. Why we have the subthreshold leakage? Because our VT is going lower and lower and lower, right? If you look into the MOSFET IV characteristics, there you will find as the threshold is going lower, the subthreshold leakage current is going higher. So that is the basic property that is coming from the structural property of the MOS as we are scaling down. And here you can see the drain leakage current. So here you can see a reverse diode, right? So drain junction is a PN junction. So there this current is going as a leakage current. There are many sources of leakage current in MOSFET. Diode leakage around the transistor and N-well, subthreshold leakage, gate leakage, tunnel currents, etc. So all these type of leakage currents contribute to the total static or leakage power dissipation, increasing 20 times each new fabrication technology. So as we go down node by node, this increases 20 times. Went from insignificant to a dominating factor. I explain this to you. As we go down, we do have the higher frequency of operation. Alongside, we have the packing density going higher. That means more room for the small transistor in the same size of the die. That means in a previous node, in a particular square area, if there are X number of transistors, now in a down node, that means a lower node, we have Y number of transistors in the same square area. Inevitably, Y is greater than X. As we grow in number, what happens? The drain junction leakage and all the other types of leakage current discussed here, as well as the subthreshold leakage, these are increasing. So cumulatively, that means we use the sum of all these leakage currents as a static leakage current. This is increasing as the number of gates and hence the number of transistors are increased. So here we are done with the discussion of the leakage power dissipation. Let's move on to the next slide. Total power dissipation. The total power dissipated in CMOS circuit is the sum total of dynamic power, short circuit power and static or leakage power. Design for low power implies the ability to reduce all the three components of power consumption in CMOS circuit during the development of a low power electronic product. So when we design for a low power, that means we have to reduce all the three components that we have discussed in last 3 slides. The general aim of the low power designer is to reduce the current consumption by minimizing the supply voltage, circuit complexity, clocking frequency, DC current source value and capacitance of the switching nodes. You have seen the load capacitance we have shown in some of the figure couple of slides back. All these points have to be taken care because supply voltage we have to minimize for the dynamic power dissipation. Circuit complexity has to be reduced so that the number of gates and hence the number of CMOS pairs are less and hence the leakage current caused by those CMOS pair is less, as well as we reduce the clocking frequency or we adjust the clocking frequency in such a way that the power is less dissipated when the device is not in use or in use in the active state. And DC current source values you also have to reduce and the capacitance of the switching node. Capacitance are acting as the load, so definitely the capacitance, the parasitic capacitance and the resistances have to be minimized, otherwise the drop across those R and Cs will increase and hence the increase in the power will happen. Circuit functions that are continuously in operation best implemented in analog circuitry. So whichever circuit those are in continuous operation, they are done through the custom or semi-custom method. That means with the analog method of design. We do also have a episode on differentiating the custom and the semi-custom designs and the full custom designs. Please watch that episode itself in this FAQ playlist. We have that. Link is provided in the description. Here we are done with the total power dissipation and let's move on to the next slide. Low power optimization. So far we have discussed about different components of the CMOS pair which is contributing to different type of leakage, which as a result of the summation give a lot of power dissipation in the entire chip. Now this slide onwards we will talk about different methods about through which the VLSI designs are made power efficient. Power management, how it is done? We use power gating. Next we use clock gating. Next we use dynamic voltage scaling. Next we use dynamic frequency scaling. We use multiple threshold voltage in the design. We use multiple VDD in the design. And we use isolation cells to isolate different power domains inside the same chip, maybe with multiple VDD or multiple VT. Next, we use the retention flip-flops to save the states for turning before turning off the block and restore of the states after turning on the block. Here, let me tell you something. In power management unit, what is a power management unit published in this FAQ series? We have talked about these things. Okay, this is already covered. The link of the video is provided in the description. Please watch that episode for all of this. And here today we will talk about all these things which are not discussed yet any in the episodes. Let us proceed to the next slide. Clock gating. Clock network in a chip consumes 30 to 50% of the dynamic power. We have talked about the dynamic power and you know it by now. Here is the clock gating diagram. What is the kind of clock gating? So we do have a gating logic through which we pass our main clock and we use a enable to control this. That means whether this line will be enabled or not. Next, the output goes to the gated block. That means the gated functional block where the gated clock is. Next, our output goes to the gated functional block where the gated clock is supplied for power optimization. And also we do have our main clock going to the regular blocks which do not need this power optimization. So this is a kind of pictorial representation or infographics that you can use to understand what is the clock gating. Now, in clock gating, the clock is temporarily turned off or switched off power domains, blocks through a control signal. So the control signal is nothing but the enable signal. This control signal can be inserted by the RTL designer or inferred by the synthesis tool through automated clock gating. So when you do this through RTL, right, you have to use the UPF. I have already told that we have a series on UPF. In case you do not know, please go ahead in the playlist page and watch that series. The crucial part of the clock gating depends on the choice of the right control signal for gating. Too much of clock gating can do harm than good as it may lead to increased dynamic power consumption. So if we do the too much of gating, so the complexity increases and because of that complexity, the dynamic power and some other powers may get increased. Hence, judicial decision of the clock gating is required. So this is done by the designer and through couple of iteration back and forth in the entire design process, that what should be gated and what should not be gated, how much of the circuitry should be gated and how much should be relieved from it. So here we are done with our clock gating description. Let's move on to the next slide. Dynamic voltage and frequency scaling, abbreviated as DVFS. The DVFS technique modulates the dynamic power based on the variation of voltage and frequency. How? This is how. This is the infographics that will help you to understand. This is generally used when the workload is not CPU bound. So whatever workload is there, it is not tied with the CPU. So here you can see at VDD1. So this is the VDD level, right? And this is our clock. So here you can see at VDD1, we have frequency 1. Right? I have made it with different colors so that you can easily identify, and I have kept the same color here, the green, and here it is green. And next at some point we change over to VDD2 and you can see the frequency has changed here. You can see by the spacing of the clock cycles, that means the period, that means the clock period is different for this frequency and this frequency. So both are different. So here also I have kept the convention of the color red and red together. And here after certain time we resume our previous VDD and hence we resume the frequency 1. So you can see there is a mapping. With VDD1 we are going with frequency 1, with VDD2 we are going with frequency 2, and with VDD1 again we are having the frequency 1. That means this is the clock frequency, this is the clock. This is our clock and this is our VDD. We have shown only 2 VDDs here. In actual practice, there might be multiple VDDs and multiple frequencies. But for your easy understanding, we have kept it simple. Choice of the operating frequency generally back calculated from the workload and turn around time of the task. So there is a back calculation of the operating frequency from the workload and turnaround time. When the voltage is constant, the scaling down of the frequency might not work. So if this voltage level is constant, we cannot do these changes. We cannot, because it's a mapping. with VDD1 we have frequency 1 and with VDD2 we have frequency 2. So the voltage changes, the frequency changes. For static VDD we cannot do it. So here we are done discussing about the dynamic voltage and the frequency scaling. And before moving to the next slide, I would like to talk as we change our clock frequency, right? CMOS power dissipation, the three types of CMOS power dissipation we have talked earlier also get impacted. You know already by this slide, right? And once we switch over to the different frequency here, that is impacted again. And once we come back to our original frequency, the impact is same as this frequency, the power dissipation, that is the three different components of the power. We are done here. Let's move on to the next slide. Power gating. Understanding of the power modes is required for deciding the power down or power up sequence. So power up means whenever the circuit is switched on, different part of the circuit is not switched on simultaneously. However, there is a time gap or there is a sequence in which all the blocks inside a circuit, that means inside the entire chip, are turned on. For a human readable or human sensible time, it is very less. You cannot have this, but in a simulation time, you can have maybe couple of nanoseconds apart. So here are typically some of the things that goes on when we power on a chip, right? In the diagram, let us come to the next point. Retention flops are used to retain states of the switched off blocks. Alternatively, in the some cases, store and restore registers are also used. So we have entire episode on the retention flop. What is a retention flop? Inside this FAQ series itself, please go ahead and watch that. So here you can see the power up sequence. So there is a clock is there, the enable goes on, we have the VDD. After that, if you take a slice here, if you take a slice here, and if you take a slice here, you can see that all the things are not happening simultaneously, and they are a couple of nanoseconds apart, this from this and this from this. Okay, so all these things happen inside a circuit. We don't have a proper circuit here, for example, and hence we cannot say specifically about all these things, but generically you will see such kind of picture where the clock is started, the enable is there, the VDD is there, the reset is there, some other maybe 4-5 waveforms are also there. In actual case, you will see that power up sequence or the power down sequence will be controlled, and hence the power gating is controlled. That means power is provided to different blocks to this power gating. A challenge with the power gating is the wake up time required for the system to be completely operational. So the power on sequence, the power up sequence, this is the challenge. That means how much time it takes to resume the operation. That means we are using retention flops to retain the states, and we switch off that block, or automatically the block is switched off, and after certain time that block has to be turned on, and after it is turned on, how much lag is there to go to the states which we are taking back from the retention flops. That is a thing that the designer has to take care, and during the VLSI design. That's all here we have to talk about the power gating. It's a method and we cannot go far more detail in this a single slide. Here we are done. So let's move on to the next slide. Summary. Let us summarize whatever we have discussed so far. Power consumption is an increasing challenge in the sub-nanometer VLSI designs, and you know there are three different parts of the power dissipation itself. An ASIC might contain several power optimization techniques such as clock gating, which is most popular, most widely used, dynamic power, multi-VT cells to reduce the leakage power. As we are going down the technology node, drastic power optimization methodologies like dynamic voltage frequency scaling, DVFS, multiple VDD and power gating are used. So here we're done with our summary also. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below. And bye for today.